Hi everyone. In this video we were gonna talk about standing waves. One way that standing waves can form is if two waves are moving in opposite directions and they interfere with each other. So these are two traveling waves. They have the same speed, but they're moving in opposite directions. So one example of that is y1 and y2 over here, two functions of x and t. And you can see that these are traveling in opposite directions. So one of them, the first one is a right moving wave. So right moving, and how do I know that this is a right moving wave? Well, the wave function looks like y1 x comma t is equal to a sine kx minus omega t. And I've particularly chosen a right moving harmonic wave because it makes a lot of this kind of a little bit simpler. So this wave is moving with phase velocity v is equal to omega over k, right? And now if we choose another wave, this y2x comma t, which is left moving, so now I pick a left moving wave, right? So this left moving wave is now y2x comma t, which is equal to a sine kx plus omega t. And since the phase is kx plus omega t, the wave speed is the magnitude is the same. It's omega over k, but there is a negative sign. The additional negative sign tells you that this is moving to the right, but this one is moving to the left, right? So if I can draw here, yeah. So that's the direction of motion. This is the direction of motion for the left moving wave. This is the direction of motion for the right moving wave. Okay, so now let me show you a plot for these waves. So particularly I have plotted this y1 x comma t as a function of time, and if I make it, if the function runs properly, there you go. It's now, you can see that this is moving to the right. And then similarly, I can also design y2x comma t, and that's moving to the left. Okay, so it might help to look at these two together. So these dashed curves over here represent the two right and left moving waves. At the very beginning, they're exactly the same waves, right? They're not at time t equals 0, for instance. If I put in time t equals 0 in my expressions, I get the same exact wave. So now if I play them together, you can clearly see that the red is moving in one direction, but the blue is moving in the other direction. Right, okay, so they're moving in opposite directions, and now we're going to interfere them. So if I interfere them, remember, superposition principle tells me that the interfering wave function will be just a sum total of the two wave functions. So y of x comma t, so now we're going to use superposition principle. So superposition will tell us that y of x comma t is equal to y1 x comma t plus y2 x comma t. Okay, so now let's just simply add these together. A sine kx minus omega t plus a sine kx plus omega t. Okay, so if we add these two together, the a factors out, so we have sine of kx minus omega t plus sine of kx plus omega t. Okay. All right, so now let's actually use our the formula that we learned earlier for trig, right? So there was a trig relationship, which is sine of theta 1 plus sine of theta 2, and it turns out that this is equal to 2 times sine of theta 1 plus theta 2 divided by 2 multiplied by cosine of theta 1 minus theta 2 divided by 2. All right, so let's apply that here. So all we have to do is take the first part will be, there will be a factor of 2, and this factor of 2 is coming from this factor of 2 over here, right? So if I put that factor of 2 in, then I get 2 times a, and then the first function is a sine, so inside the sine we add the two phases together, so kx minus omega t plus kx plus omega t, and then divided by 2. And the next part is a cosine, and inside the cosine we have to subtract the two phases, so we have kx minus omega t minus kx minus omega t divided by 2. And the second part over here is a negative omega t because you're subtracting off the phase, which is negative kx plus omega t. So if you distribute that negative sign, you get negative kx minus omega t. Okay, so now let's look at this form. Clearly within the first one, there's a negative omega t and a positive omega t, so these will cancel. And inside the second one, we have a positive kx and a negative kx. So clearly these will also cancel. Okay, so the final answer that we get looks like 2a sine kx. Okay, and this is sine kx because you have kx plus kx, which is 2kx divided by 2. So the 2 cancels and we get 2a sine kx, and then for the cosine part of this, we get cosine omega t. And again, this is negative omega t, negative omega t. So you get negative 2 omega t divided by 2. So the 2 cancels. And remember, cosine of negative theta is just equal to cosine of theta. So cosine of negative theta is equal to cosine of theta. So we can just use that, and we get 2a sine kx cosine omega t. Okay, so this is an example of a standing wave. And the reason why this is a standing wave is because if you look at, if you compare it with our right moving or left moving waves, they had kx minus omega t or kx plus omega t. Okay, but now if I look at this one, this has neither kx minus omega t nor kx plus omega t, right? So this is not a traveling wave. Okay, so this is an example of a standing wave. And let's actually look at the plot. How does this behave? What does it mean to be a standing wave, right? So this was going back to our original plots. The figure here with the dashed lines, that shows us the traveling waves, and we remember that they are traveling in opposite directions. And now if we go to our next figure, this is where the two traveling waves, I will make them interfere, and let's see what happens. So watch carefully the purple curve. The red and the blue curve are moving in opposite directions very clearly, and the purple curve, that's just oscillating up and down, right? Okay, so that's when we evolve over time. I have another figure. So here you can see how the traveling wave behaves as time changes. So all these dashed lines are different versions of the same wave at different times, right? So as time goes on, where the traveling wave would have just either moved to the right or to the left, the standing wave oscillates back and forth, up and down at the same place. So now that we have an idea of how standing waves may form by interference between two waves that are moving in opposite directions, let's sort of think about how can the two waves be moving in opposite directions. So one way that can happen is via reflection, right? So reflection. So if let's say you have an original wave that's let's say moving to the right. So this is my original wave. It's moving to the right, and then it encounters a wall or some sort of barrier somewhere, and it gets reflected. So the reflected wave will now look something like this. Okay, so now generally the incident, so this one is my incident wave, this is my reflected wave. Generally, the incident and reflected waves may not have the same phase, or in other words, at the point of reflection, there might be a phase difference. And if there is a phase difference, our formula, our original formula for the wave, this formula over here, 2a sine kx times cosine omega t, that has to be changed. But the idea stays the same. the idea that you have a standing wave is still there. So now we'll look at a particular example. A particular example for this is waves in a pipe. So different ways that standing wave patterns can form in a pipe um, happens because of reflection. So let's talk about a closed pipe. So let's think about a pipe that is closed, and usually closed pipe refers to a pipe that is open on one end. So if I have a pipe that looks like this, right? And often these pipes appear in musical instruments or organs, stuff like that, right? So if let's say that you either blow air into this or in some way there is a flow of air in the pipe, then what will happen is there's essentially some sort of wave that's going in, and at the end it's probably going to get reflected and come back. And these two waves are now moving in opposite directions, and they're going to interfere with each other. And when they interfere with each other, we will get a standing wave. And a pretty common example of that standing wave is this picture over here. So you can think of the waves as sort of going in, reflecting, and coming back and forming an interference pattern. And the idea for this interference pattern then would be that the pressure, so this is essentially a pressure wave because sound in air moves as pressure waves. So air pressure at the open end of the pipe must be similar to the atmospheric pressure that is outside or close to the atmospheric pressure. So we'll have a pressure antinode over here, very close to the end of the pipe. It's not exactly at the end, but for our purposes, we are going to assume that the antinode is exactly at the end of the pipe, right? And at the closed end of the pipe, of course, if you look at just the closed end of the pipe over here, that closed end of the pipe must have a pressure node. That is, the pressure must go to 0 at that end. And because of this condition, the reflected end, so if I just turn the pipe around like this, so essentially we have a wave that is going in and it's getting reflected, and when it gets reflected, it turns around like that and comes back. Okay. So then there are only few options for us to have different kinds of waves in there, right? So for instance, this is an example. And then the other one that one could do is if the wave just goes in, gets reflected, comes back like this. All right. And another one that one can do is it bounces a couple of times within the pipe and then comes back out, right? So these are a few examples. There are lots more available, but if you think about it, what it looks like is that, so if I drew one single waveform like that, this is one wavelength, right? So whatever sound that is coming out of this has a wavelength that looks like this when it oscillates once. Okay. All right. So now if I look at this particular situation, well, so from the point over here at the end of the pipe to the point over here, that looks like just sort of from here to there, right? So that's half the wavelength. Okay, that's lambda over 2. And the rest of it looks like another quarter of the wavelength. It kind of looks like this part, right? So this part, so that's a lambda over 4, quarter of the wavelength. Okay. So that means that the standing wave pattern that formed inside this pipe over here in this first situation has length equal to lambda over 2 plus lambda over 4. And that must be equal to the length of the pipe itself, right? Because lambda over 4 is this part, lambda over 2 is this part. And if we add these two together, then we get the full length of the pipe, right? So if I have a pipe of a certain length, then there are only certain combinations or certain wavelengths of sound that can form standing waves in that pipe. One example being if the length of the pipe is equal to lambda over 2 plus lambda over 4, which is also equal to 3 lambda over 4. Okay, so that's for this first figure. For this figure, it looks like it's just lambda over 4 equals L, right? This part, so L is the full length of the pipe, and the the first node to the first antinode, that distance is equal to a fourth of the wavelength. Okay, so that's for the second scenario. This third scenario looks like there is each of these is a fourth of a wavelength. So fourth of a wavelength, fourth of a wavelength, etc. And if we keep going, then we have 1, 2, 3, 4, 5. So this is 5 lambda over 4 is equal to L, right? Now notice a pattern. So there's 3 lambda over 4 here, but we could have started with this lambda over 4. So there's lambda over 4, then 3 lambda over 4, then 5 lambda over 4. So now you can sort of imagine that if we keep going with this pattern, then we will end up with a situation which looks like L is equal to some odd multiple, so 2n minus 1 times lambda over 4, where n can take any positive integer value. So n equals 1, 2, 3, etc. are allowed, right? So if n equals 1, then we get 2 minus 1, which is 1 lambda over 4. So that's our first situation over here. N equals 2 will give us 3 lambda over 4, and so on, right? Often this the case where lambda is largest, right? So this is the case where lambda over 4 equals L. That gives us lambda is equal to 4L over 1 in this case. But if I plug in, just rewrite this equation, it looks like lambda equals 4L over 2n minus 1. So largest lambda is for n equals 1. Okay, but the speed of sound, v sound, is the same for any wavelength, which means, and v sound is equal to frequency of sound times wavelength, right? So that tells us that frequency f for, so let's give this an index, lambda n, because lambda changes as n changes. So similarly, fn will be equal to v sound, right, divided by lambda n. So that will give us fn is equal to 2n minus 1 multiplied by v sound over 4L. Okay. Okay, so for n equals 1 then, so f1 is equal to v sound over 4L. f2 for n equals 2, this is equal to 3 times v sound over 4L. So this is the minimum frequency, right? So this is the min frequency. This is a multiple 3 times the min frequency. And as we go higher and higher, we will get odd multiples of the minimum frequency. So this minimum frequency is often called the fundamental frequency. So this is the fundamental frequency. Okay, so for a closed pipe, the fundamental frequency is equal to the speed of sound divided by 4 times the length of the pipe itself. All right, that's the fundamental frequency. And as we go higher and higher, these are called harmonics. So this would, in some situations, be called the first harmonic. There's nothing between the fundamental and the first harmonic. And then there'll be second harmonic would be 3 times, or the first harmonic is 3 times the minimum frequency. So the second harmonic in this case is going to be 5 times the minimum frequency, and you'll keep going higher and higher, right? So fundamental frequency, first harmonic, second harmonic, third harmonic, etc. Okay, so that's the idea for standing waves in a closed pipe. So this example was particularly for closed pipes. Okay, and so if you know the length of the pipe, as soon as you know the length of the pipe and speed of sound, so these two will tell you all the different frequencies of sound that you can create with that pipe. and the particular answers are these F1, F2, and higher order situations. So for any n, you can use this formula over here. Fn equals 2n minus 1 times v sound over 4L. That should give you all the harmonics for a closed pipe. Okay, so that's for a closed pipe. Now the next example that I have is for an open pipe. So what is an open pipe? Okay, so this nomenclature sometimes seems a little bit confusing to me. Closed pipe means a pipe that is closed only on one end. And that's because if you want to make sound with a pipe, well, you have to blow air into it. So you need one end that is open, right? So closed pipe just means one end of the pipe is open and the other end is closed. For open pipe, the open pipe just means that both ends of the pipe are open. Okay, so let's now talk about open pipes. So open pipes are very similar, right? The idea is very similar. We'll have standing waves, and this time, in order to form the standing waves, again, we will need two waves that are traveling in opposite directions. So what we will do is, let's say that there is, again, the condition is that the air pressure outside over here, this must be sort of the atmospheric pressure, right? Because there's atmosphere outside. And so these have to be pressure antinodes, okay? Antinodes of pressure, right? So both here, over here, as well as over here, we will need antinodes of pressure. Okay, so in order to get an antinode of pressure and also have a wave, we need nodes somewhere in the middle. So we essentially, the idea is to count the number of nodes. So the easiest way of doing this is to put one node in the middle, right? So that's a pressure node. Pressure node means that the pressure goes to 0 over here. Okay, so that's an example of a wave, standing wave pattern that can form inside an open pipe. And so we'll do exactly the same idea again. This is the length of the pipe L. So for an open pipe though, now if you look at this, let's go back to our waveform, wave pattern, right? So this is the pattern for a full wavelength. And what we are looking at over here inside the pipe is just this lambda over 2, right? So this portion is essentially just lambda over 2, okay? So that tells us that for this open pipe, L, the length of the pipe has to be equal to lambda over 2. All right, so that's one example. What else could we do? Well, we can take another situation where there are two nodes inside the pipe, right? So something like this. Okay, so this is not a perfect picture. The nodes are going to be at the same level because these are all zeros of the pressure. Okay, so there are two nodes, but if there are two nodes, then now we can again partition this, right? So this is a lambda over 2, and this one is also another lambda over 2. Okay, so this makes it 2 times lambda over 2. Okay, what's the next situation that we can create? Well, then we'll need 3 pressure nodes inside. So this is, so it oscillates like this, comes back like that, and goes there. And so we have, here is my first node, right? Comes back and gets me my second node, and comes back, gives me my third node, right? So these are 3 nodes. And now again, if you partition it, you can see that there is 3 lambda, or 3 parts, which are each lambda over 2, right? Okay, so that tells me that L has to be equal to some multiple, integer multiple of lambda over 2. So L equals n lambda over 2, where n is equal to 1, 2, 3, etc. Okay, and we can play exactly the same game. We know then this tells us that lambda is equal to 2L over n. So let's put a subscript n over here. As n changes, lambda changes. As n gets bigger and bigger, lambda becomes smaller and smaller. So as lambda decreases, the frequency increases, because we know that frequency Fn is equal to V sound over lambda n. Okay, so let's plug that in. So V sound over lambda n, so that's going to give us n times V sound over 2L. Okay, so this is our master formula for open pipe. So this is only for open pipe. You can see the difference between open pipe and closed pipe, right? So in the case of closed pipe, it was Fn equals 2n minus 1 V sound over 4L. This time for an open pipe, we have Fn equals n times V sound over 2L. Okay, so what are the different kinds of frequencies? Well, first of all, we can have Fn n equals 1. So F1 is equal to V sound over 2L. So this is the minimum frequency, and it's often referred to as the fundamental frequency. Now, you may see some books use a slightly different notation where they call this F0. So then you'll have to change what prefix goes over here. So F0 might refer to the fundamental, and then F1 might refer to the first harmonic, etc. But in our case, we'll just refer to F2 as the first harmonic. So F2 is going to be equal to V sound over L. This is twice as large as the fundamental, so this is our first harmonic. Okay, and then higher harmonics will just be, for instance, F3 will be equal to 3 times V sound over 2L, right? So this is 3 times as large as the fundamental, and this is going to be our second harmonic. And so you can now find all higher harmonics just by using this formula over here. So another example of standing waves is waves on a string. So think about a string that is sort of attached to, let's say, a wall over here, and this is my string, and then I'm holding this end with my hand, and then I start moving my hand up and down like that. So what's going to happen is there's a wave's going to form. So when a wave forms, it's going to start traveling, and once it reaches the wall, it's probably going to get reflected, and it's going to come back, and so this will form a standing wave pattern, right? So now this standing wave, of course, again, the frequency of the standing wave cannot be just anything. It's restricted, just like when we discussed our pipes, the frequency was restricted by the length of the pipe. Here, the frequency is going to be restricted by the length of the string itself. So let's think about it. Here, in this particular picture, we have a amplitude antinode at the place where, right? So this is an amplitude antinode at the place where I am sort of moving my hand vigorously up and down, right? So I'm letting the amplitude of the string to go positive and negative, so it's an amplitude antinode. And then at the point where the wave is fixed, or the string is fixed to the wall, there the string doesn't have the ability to move up and down, which means that this point must be an amplitude node. So any wave that forms in the middle will have to satisfy these two conditions, these two boundary conditions, we call it sometimes, that there is a node at the end on the wall, and then the other end, the free end, has an antinode, which means there are only so many patterns that we can allow. The first one of them that we can allow is if there is just one node and one antinode, right? So this kind of a pattern. So now again, if we go back to our picture for wavelengths, so this is one wavelength, right? Pictorially, that's one wavelength, which means this segment between between one node and the next antinode is just the wavelength, fourth of the wavelength, lambda over 4, right? So coming back to this example, this length must be lambda over 4, but this is also equal to the length of the string. So L here is our length of string. Okay, so this is one example. In this example, lambda over 4 is equal to L, which also means that lambda is equal to 4L. And so this is the largest wavelength of a standing wave that can form on this kind of a string, where one end of the string is fixed and the other end of the string is able to oscillate back and forth, right? But there are other situations that can happen, right? So the two boundary situations, one is the one over here. If you look at this left-hand side panel over here, this point over here, that point represents the end of the string that is tied to some wall, let's say that's anchored to the wall. And the other end is where I am sort of with my hand making it go back and forth. So that's the the first end is the node, the other end is the antinode. Now the question is, how many other ways can we form the same thing? Well, we can put as many nodes as possible in between the node at the wall and the antinode in my hands, right? So the next obvious situation is shown in this picture, and in this picture we have so the distance from one node to the next node is lambda over 2, right? So lambda over 2 plus lambda over 4 represents the distance from that node to the nearest antinode, right? So that's lambda over 4, and sum total of these two have to be equal to the length of the string, right? So this means that 3 lambda over 4 is equal to L. And so now we can work out the general situation, right? So if you have, essentially we had 2 nodes, and that gave us 3 lambda over 4. So if we have 1, 2, 3 nodes, that's going to give us 5 lambda over 4. And in general, we can have 2n minus 1 lambda over 4. So some odd multiple of lambda over 4 is equal to L, right? So the first case is just lambda over 4 equals L, so that this factor is 1. The next one is 3 lambda over 4, so this is 3, and then so on and so forth, right? And so one can then write lambda n. So lambda changes with n, right? Remember, L is fixed. Length of the string, you have fixed the length of the string. So lambda n is equal to 4L divided by 2n minus 1, where n is equal to 1, 2, 3, etc. Right? And so this is essentially the formula for wavelengths of standing wave patterns. Right? So that's the wavelength of the nth standing wave pattern that can form on a string with these particular boundary conditions. The boundary conditions are that one end of the string is fixed, the other end of the string has an amplitude antinode. Okay, so that's that happens when at least one end of the string is free. But now let's see what will happen if both ends of the string were fixed. So if both ends of the string are fixed, and then think of it as a string which I plucked somewhere in the middle, right? So here is a wall, here is another wall, and we have a string that is attached to them, to the two walls, right? And then I go to the middle over here, and I lift this string up a little bit and let it go. So then it's gonna sort of start doing this kind of an oscillation, right? Back and forth between that, right? Now there's several situations, there's different ways of actually striking or, sort of making this string oscillate. Of course, the different cases should always satisfy the condition that the string cannot be moving at the two ends, right? So that means the longest wavelength then you can have is this scenario here, where there are the two nodes and there is one antinode in between the two nodes, right? So for this, then we have lambda over 2. The distance between two consecutive nodes is lambda over 2. That is equal to the length of the string. Okay, and the next situation I show over here, so there's an additional node in the middle, right? So as soon as there's an additional node in the middle, you're adding another lambda over 2. So for this situation, we have lambda over 2 multiplied by 2 is equal to L, right? So that tells me that lambda is equal to L. So for this first situation, though, lambda was equal to 2L, right? So you can see that lambda is decreasing slowly, right? So in general, then, for a situation like this, we will have L is equal to n lambda over 2, right? And so L is equal to n lambda over 2, which means lambda n is equal to 2L divided by n. And so that's the general situation where n is equal to 1, 2, 3, etc. One a particular example where strings can appear is if you have a musical instrument, right? So musical instruments um, like a guitar or a violin. So those are a little more involved situations, but the basic idea is the same, that you're creating some standing wave pattern on the string of the stringed musical instrument, and that associated with that standing wave there is the frequency of sound and the sound that you hear. Okay, so I hope you enjoyed this video.